Today, we are talking about section 3.3, sampling from a small population. So this, things to take notes on are sampling with and without replacement, independent versus dependent draws, and sampling rule of thumb. So the sampling rule of thumb is going to be the main thing that's going to show up again and again and again. And the other stuff before that is just sort of building towards a reason why. So later on in the course, we're going to, when we get real data, real statistics, we're going to ask, can we assume normality here? And one of the things, or can we assume independence? And one of the things we need to check for is if the sample needs to be big enough, but sometimes you can have a sample that's too big. And you got to either go for like a sample and then infer, or you just got to like do a census and ask everyone. And so there's this weird middle ground where your sample is too big. It becomes like you get more than 10% of the population in your sample, then you mess up some of our assumptions about independence. And that's what we're going to explain in this section. So when sampling with replacement, you put back what you just drew. So imagine you have a bag with 5 red, 3 blue, and 2 orange chips in it. What is the probability that the first chip you draw is blue? Well, it's 3 out of 10, so 0.3. Now, suppose you indeed pull a blue chip out of the first draw. If drawing with replacement, what is the probability of drawing a blue chip in the second draw? Well, with replacement, it means I drew the blue chip and then I put it back. So now the probability is still 0.3. Okay. So suppose you actually pulled an orange chip in the first draw. If drawing with the replacement, what is the probability of drawing a blue chip in the second draw? It's still 0.3. Okay. So if drawing with replacement, what is the probability of drawing 2 blue chips in a row? It's independent. So we get to multiply them. Okay. However, when drawing with replacement, probability of the second chip being blue does not depend on color of the first chip, since whatever we draw in the first draw gets put back in the bag. So the conditional probability of like the given doesn't matter. In addition, this probability is equal to the probability of drawing a blue chip in the first draw, since the composition of the bag never changes when sampling with replacement. Okay, so the key takeaway is when drawing with replacement, like putting things back after you draw them, draws are independent. Okay. However, most normal samples of populations are drawing without replacement. So when you're drawing without replacement, you do not put back what you've taken out. So suppose you drew a blue chip in the first draw, and if drawing without replacement, what is the probability of drawing a blue chip in the second draw? So we take our first draw, and then our second draw, we have 1 less blue chip. So then the probability of getting a second blue chip, given that you got the first blue chip, is 0.22, because it's 2 out of 9 instead of 3 out of 10. So if drawing without replacement, what is the probability of drawing 2 blue chips in a row? It's 0.3 times 0.222, so times 0.22, which is 0.066. Okay, so when drawing without replacement, the probability of the second chip being blue, given the first was blue, is not equal to the probability of drawing a blue chip in the first draw, since the composition of the bag changes with the outcome of the first draw. So probability of blue given blue is not equal to probability of blue. So the key takeaway is that when drawing without replacement, draws are not independent. Okay, this is especially important to take note of when the sample sizes are small. If we're dealing, say, 10,000 chips in a giant bag, taking out 1 chip of any color would not have a big impact. But with small bags, it does have an impact. All right, let's do a practice question. In most card games, cards are dealt without replacement. What is the probability of being dealt an ace and then a 3? Choose the closest answer. Okay, so remember, there's 52 cards in a deck. All right, so think about it, try to come up with an answer. I'm going to provide it in 3, 2, 1. So the probability of getting an ace, there's 4 aces in the deck, so 4 out of 52. Then there's one less card in the deck, and there's 4 threes. So then the probability of getting a 3 is 4 out of 51, so it's 0.006. Why is this important? Later on, we'll need to assume independence in order for our formulas to work. If we're sampling without replacement, then the rule of thumb is sample less than 10% of the population, okay? That's it. That's the thing. You're gonna see that over and over again. You're like, Dr. Johnson, why do we have to sample less than 10% of the population? And I'll say, go back and watch the video for section 3.3. All right, this one's done.